Hello all, welcome to the next lecture on microwave engineering. So till now we have discussed the general characteristics of the waveguides. We have covered the general analysis, the solution for various field expression inside the waveguide, and also we have seen the propagation of transverse electric mode inside the waveguide. So we know that depending upon the polarization, so we get different types of mode propagation inside the waveguide. So when the wave that is you're launching, the electromagnetic wave that you're launching, if the wave is vertically polarized, that is the electric field is always perpendicular to the direction of propagation, we get transverse electric waves, right, which is also called as TE waves and TE mode waves. Okay, so we discussed the field components. What are the field components that exist in case of the TE wave, and also the characteristics of the TE waves. Right now, let us go to the next topic, which is the propagation of transverse magnetic waves. Magnetic waves. Transverse magnetic waves in the waveguide. TM waves in the waveguide. TM waves. Okay. So first we will start with the general analysis, that is the expressions, derivation of expressions of the field components for the TM waves, and then we will see the characteristics of the TM wave propagation. Okay. So firstly, right, when do we get TM waves? So we will get TM waves, that is transverse magnetic waves. So whenever we launch an electromagnetic wave that is having horizontal polarization or parallel polarization. Okay, that means, so right, if I consider this as my waveguide, so if the wave that is launched into this waveguide, okay, so if this wave is having, right, electric field parallel to the plane of propagation, or the magnetic field that is there, so this h bar, the magnetic field h bar is always perpendicular to the, right, direction of propagation or to the plane of conductors. Okay, so that is right. So as the wave is propagating, the magnetic field, the wave is like this is my direction of propagation, so magnetic field component is always perpendicular, so it is always like this. Okay, so if this kind of thing is called as horizontal polarization, okay, this kind of wave is called as horizontally polarized wave or parallel polarized wave. So whenever I incident an electromagnetic wave which is horizontally polarized or parallelly polarized into the waveguide, then, right, what happens is the resultant electromagnetic wave will have a magnetic field which is always perpendicular to the direction of propagation. Okay, so the magnetic field inside the waveguide will always be perpendicular to the plane of polarization. That means, so if I consider the magnetic field having two components, one is transverse component and one other is the longitudinal component or Z component. So because the wave propagation or the direction of propagation is along Z, which is nothing but the longitudinal direction, so magnetic field we have transverse and, right, longitudinal or Z component. So here in this case, okay, the Z component of the magnetic field or the longitudinal component of the magnetic field is equal to 0. Okay, so, right, I will get a wave when I incident electromagnetic wave of horizontal polarization into the waveguide, right? So my magnetic field will be parallel. Magnetic field will be magnetic field will be always perpendicular to the longitudinal direction or to the direction of the wave. Okay, so what that means? That means that, right, in all cases I will have only HT component, that is transverse component, because it is perpendicular component, right, and always my longitudinal component will be 0, that is Hz or H longitudinal is always equal to 0. Okay, so this kind of mode propagation, this kind of wave, right, propagation, or this mode of propagation of the wave inside the waveguide is called as transverse magnetic mode or transverse magnetic wave. The wave is said to be transverse magnetic in nature. Why? Because the magnetic field is always having only transverse component, right? The magnetic field is always transverse to the wave propagation. Okay, so there is no longitudinal component of the magnetic field. Okay, so this is the right TM wave which we discussed before also. So let us see, right, what are the field expressions, okay, and also the field pattern for this kind of wave inside the waveguide. Okay, so let us do the analysis for the TM wave, right? So now I think the point is clear, right? So whenever I launch whenever I launch a horizontally polarized wave into the waveguide, I will get right a TM wave. Okay, so what do you mean by TM wave? The TM wave means the magnetic field is always transverse to the direction of wave propagation. That means the longitudinal component of the magnetic field is always zero, and the longitudinal component of electric field exists, that is it is not equal to 0. Okay, so Hz will be 0, Ez will not be 0, so the electric field will, or the wave will propagate through the right transverse longitudinal direction, but magnetic field will have only right transverse component, it does not have right longitudinal component, that is Hz is equal to 0. So for a TM wave, right, Hz will be 0, Ez will be not equal to 0. Okay, so for this case, let us derive the expressions for the field components. Okay, that is Ez, Ex, Ey, Hx, Hy. Hz is not Hz is equal to 0, but the other components of magnetic field should exist. Then only right I get the electromagnetic wave. Okay, so what are the field components that exist, right, and what are their expressions? Let us derive them. Okay, yeah. So right, firstly let me assume a planar waveguide. Okay, so let us assume a planar waveguide. Okay, so placed along z-axis, so one plane is placed at x is equal to 0, another plane is placed at x is equal to d, so that is the separation between these two is d. In earlier derivations we assume this as a, either way it is right up to us. Okay, we can assume it as x equal to d or x equal to a, no issues. Okay, so let me take it as d here. Okay, so the spacing between the two planes is d. Okay, right, so as I said, this is right placed along z axis, so the longitudinal right or the wave direction is along z. Okay, so the wave propagation is along z. Okay, right, and this is the thing. Okay, now as we discussed with the transverse electric case, here also, right, because you are assuming infinite planes, okay, the waveguide is same, right? So the waveguide is same, so the planes that you assume are infinite extended in y direction, along y direction. Okay, so planes that I consider is infinite plane. Okay, so therefore along y direction, right, the variation or the boundaries are 0. Okay, so there are no boundaries assumed along y-axis because the plane is extended right over a y of infinity. So therefore, right, there will be no variation of any component along y-axis. So always d by dy is equal to 0 and hz is also equal to 0. Okay, so these two right are the assumptions that we get or the conclusions we get from the orientation of the waveguide. Okay, right. Now as we said, the wave propagation happens along z-axis, right? So therefore, right, the expression for wave from the Hertz equation, we can write it as del square Ez is equal to right omega square mu epsilon into Ez. This is the Hertz equation we get. Okay, so there is no Hz, so Hz is equal to 0. So now wave equation can be written only in terms of electric field. So I get like this. Okay, again we know that del square is equal to dou square by dou x square plus dou square by dou y square plus dou square by dou z square. Okay, but dou by dou y is equal to 0, so we get del square is equal to dou square by dou x square plus dou square by dou z square. Okay, so let us substitute that here. Yeah, let us rub this also. Okay, yeah, so okay, substituting here dou square by dou x square into Ez plus dou square by dou z square into Ez. Okay, is equal to minus omega square mu epsilon into Ez. Okay, so this is the equation we get, right? Now, right, as we discussed before, okay, dou square by dou z square, we assume it as gamma square. Okay, so which is a propagation constant, so we assume it as gamma square. So if I write like this, okay, dou square by dou x square into Ez plus gamma square Ez. Let us bring this also to this side. So what I get is omega square mu epsilon into Ez is equal to 0. So from this, dou square by dou x square, okay, into Ez plus, so let us take right these two as together, we get omega square mu epsilon into Ez is equal to 0. Okay, so right here what I get, dou square Ez by dou x square plus, let us assume this as some constant which is h square. Okay, so right, let gamma square plus omega square mu epsilon is equal to h square. So I write it as h square into Ez is equal to 0. Okay, so this is the equation that I get for the wave, right? Wave equation. Okay, from the Hertz. Okay, so dou square Ez by dou x square plus h square Ez is equal to 0. This is the wave equation for now. Okay, now, right, we can get the value of Ez, right? We can get the value of Ez, okay, by solving this, right, equation, which is a second order differential equation. So, right, writing the general solution, okay, by using the concept of general solution, right? So, let us write the general solution for this. So, Ez will be equal to, it is a second order differential equation. It has two roots, right? The variable is x. So, in terms of x, we have to write. So, let us assume that C1 is a constant. C1 into cos AX is one root plus, right, C2 into cos AY. Sorry. C2 into sin AX. Okay, sin AX. So A is again a constant, C1, C2 are constants. This is the general solution I will get for Ez. Okay, for Ez, right? So, okay, just a quick repetition. So, because for a TM wave, Hz is equal to 0, the wave will have only component of Ez. Okay, so we have taken the equation, wave equation, del square Ez is equal to minus omega square mu epsilon into Ez. So from that, del square means dou by dou x square, dou square by dou x square, dou square by dou y square, dou square by dou z square. But here for the planar waveguide, dou by dou y is equal to 0. So therefore, I get del square. Now I written that. Again, we have assumed that dou square by dou z square is equal to gamma square, isn't it? So we have assumed it as gamma square. We have substituted it. Okay, we got the expression. Okay, right. Now from that, what is the next thing that we did? We took them to one side. So we have assumed gamma square plus omega square mu epsilon as some constant h. Okay, so I got the equation like this. Now this is a second order differential equation. So it will have two roots. Okay, so the general solution, writing the general solution, I will get like this. Ez is equal to C1 into cos AX plus C2 into sin AX. Okay, right. Now from this general solution, right, okay, so as I told you, right, if I want to do the analysis of any mode inside the waveguide, so we will follow the same pattern as that of general analysis. Firstly, we will calculate the components of, right, the longitudinal components or the components along the direction of wave propagation, namely Ez and Hz. Okay, so we got Ez and Hz. Hz is 0, Ez component is gone. Now from this, right, next what I have to do, I have to apply the boundary conditions if possible. Okay, after that, next what I have to do, I have to obtain all the other components. What are all the other components? Right, transverse components, Ex, Ey, Hx, Hy. Okay, so let us do that one by one. So let us apply the boundary conditions here and then we will continue, right, with the other cases. Okay. Okay, so right. So from Ez, let us calculate the other components. So firstly for Ex, okay. So Ex is equal to, right, the expression that we have, the general expression that we have from the general analysis. Ex is equal to minus gamma by h square into dou Ez by dou x minus j omega mu by h square into dou hz by dou y. Okay. So from this, right? Okay, we have got the Ez value. So minus gamma by h square into dou by dou x of Ez, we got it as sin cos c1 cos ax plus c2 sin ax. Okay, right? Minus, so because hz is 0 and dou by dou y is also 0, so we get 0 here. Okay, so this is equal to minus gamma by h square into, so when I differentiate, so firstly c1 into a into, right, c1 into a into cos of ax is nothing but sin ax, so minus sin ax into a, already I have written. Okay, next plus, so what is the other term I get? So now here when I differentiate this, c2 into, so differentiation of sin is cos a cos ax. Okay, so this is the expression for ex. Okay, so ex is equal to, right, this is the expression that I get. Okay, yeah, so let me write it here. Okay, so ex I got as ex is equal to minus gamma by h square into a c1 sin ax minus will be there plus c2 into a cos ax. Okay, right. So we got, right, the second expression, the second field component. So we have observed that ex exists and the value of ex is this thing. Okay, right. Now similarly, let us calculate Ey. What is Ey? Right, Ey is equal to, so general expression minus gamma by h square into dou by dou y of ex, ez. Okay, right, minus j omega mu by h square into dou by dou x of hz. Okay, so this is the expression that we have, general expression from the general analysis. Again, I am writing the equations directly for Ex, Ey because all these things we have derived in the general solutions. So you must be aware of that. So kindly watch that video. Okay, fine. Now from this, let us substitute the values. So here dou by dou y is always 0. So this is 0 and dou by dou x of hz is also 0. So 0 minus 0 or 0. Okay. So this complete term vanishes. Okay. So therefore, right, the other term ey vanishes. So we got ez, ex, but ey is equal to 0. Okay. So the third expression is derived. Okay. Right. Now let us go to the next term, which is, okay, hx. So we have hx is equal to minus gamma by h square. Okay, so the general expression, I am writing the general expression. The general expression for hx is minus gamma by h square into dou hz by dou x minus j omega epsilon by h square into dou hy by, dou Ez by dou y. Okay, so this is the expression. So here again minus gamma by h square into hz is 0, so this component is totally becoming 0. Similarly, right, minus j omega epsilon by h square into dou by dou y of any term is 0. So this is also equal to 0. Okay, so the third component we have hx. Hx is this, general formula is this. So here hz is 0 and here dou by dou y is 0. So this two, right, entire becomes 0. So, right, I got hx is equal to 0. Okay, right. Now next, let us calculate the final term, the final component. So that is hy. So what is the general expression for hy? Hy is equal to minus gamma by h square into, okay, so dou hz by dou y, okay, minus j omega epsilon, right, into by h square into dou ez by dou x. Okay, so this is plus. This is plus. Okay, so right, this is equal to, anyways, hz is 0, dou by dou y is also 0. So the first term becomes 0. 0 plus j omega epsilon divided by h square into dou by dou x of what is Ez? Ez is equal to C1 into cos Ax plus C2 into sin Ax. So therefore here the Ez term exists. Oh, sorry, Hy term exists because there is a term here. So this is equal to j omega epsilon by h square into, let us differentiate this. Okay, so this differentiation term, so C1 into cos Ax is nothing but minus sin Ax into A, okay, plus, right, C2 into sin Ax is cos Ax into A. So this is the right expression for Hy. Okay, so Hy term exists and the Hy term expression is given like this. Okay, so let me write it here. Okay, so Hy is equal to j omega epsilon by h square into minus, okay, a c1 sin ax plus c2, right, cos ax. Okay, a. Okay, so these are the right field components for magnetic field. Okay, for transverse magnetic wave. Okay, so right. So initially we know that Hz is equal to 0. So three components are becoming 0: Hz, Ey, and Hx. Okay, so Ez, Ex, and Hy exist for the transverse magnetic wave, and these are the field components. Okay, right. So we have completed our our analysis of the field that exists in the magnetic transverse magnetic case. Okay, done. Right. So we have taken a planar waveguide. From this planar waveguide, we have assumed inside the that planar waveguide is existing for an infinite direction along z y-axis. Okay, so therefore there are no boundaries. d by dy of any term will be 0. That is one point we got. Second point we got, because the wave will have a magnetic field that is always transverse in nature. Okay, that means the longitudinal component is 0 for EM wave. So that is Hz is equal to 0. So using these two cases and using the general analysis solution, okay, we have found out the field patterns or the fields that are existing for a transverse magnetic wave. Okay, TM wave. Right. Now the next job is to find out the constants C1, C2, and A value using the boundary conditions. Okay, so here right, we can observe that there are two for magnetic field there will be no boundary conditions, right? So there are, because magnetic field is continuous everywhere. Okay, so continuous, so we don't have a boundary condition for a magnetic field, right, in case of transverse components. Okay, so therefore Hy we cannot use. Okay, right, we can use the other two electric field components. We can have Ez and Ex. Okay, so right, we know that, okay, at the conducting boundary, at the conducting plane, right, always the electric field will be 0. Okay, so right, the electric field will not pass into the conductor. Okay, so electric field will be 0, right? Electric field will be 0 at the boundary at the conducting boundaries. So I have two conducting boundaries here, right? And there are two components of electric field. So both of them should be 0, right? Both of them will become 0 whenever at the conducting boundary is there. Okay, so that is why I can take Ex or Ez. So I'll take Ez. Okay, so let us assume that, right, Ez is my component by which I am deriving the boundary conditions. Okay, so what are the two boundary conditions I get? So Ez will be 0 whenever, right, my conducting boundary is reached. Okay, so I will have a conducting plane at 2 points. One is at x equal to 0 and other at x equal to d, isn't it? So I will get two boundary conditions. What are the two boundary conditions I get? Whenever x is equal to 0, when x is equal to 0, my Ez will be 0. Similarly, when x is equal to d, right, Ez will be 0. So let us, okay, so these are the two boundary conditions we get, isn't it? So when x is equal to 0, Ez is equal to 0, and x is equal to d, Ez also should be 0. Okay, so that is because electric field cannot pass through the conductor. So at the boundary of the conductor, the electric field should become 0. Okay, so using these two conditions, let us derive the constants. Okay, yeah. So firstly, when I take the first condition, what is the first condition? Whenever x is equal to 0, my Ez should be 0. So what is the expression for Ez? Ez is equal to C1 into cos AX plus C2 into sin AX. Now, right, when x is equal to 0, Ez is equal to 0. So I substitute Ez is equal to 0. C1 into cos of A0, that is 0, plus C2 into sin 0. Okay, so we know that cos 0 is 1. So C1 plus C2 into 0, that is 0. So this implies that C1 is equal to 0. So we got one constant, that is C1 should be always 0. Okay, so this is the expression we got right from the boundary condition. Right? Clear? Yeah. So let us substitute that here. Okay, this is the first condition. So whenever x is equal to 0, Z is equal to 0, we got C1 as 0. So we have to make this C1 0. So therefore, the modified expression for Ez is, by making C1 0, we get it as sin to AX. Okay, fine. So the now the right the form of the solution for Ez is C2 into sin AX. Now in this case, let us substitute the second boundary condition now. So whenever x is equal to d, right, again Ez value is 0. Okay. So when I put x is equal to d, again Ez should be 0. Okay. Let us substitute that. So this is 0 whenever sin, okay, AD, right, C2 into sin AD. So here I have two possibilities. One is C2 can be 0 or otherwise sin AD can be 0. Isn't it? So this product, the product of these two should be 0. That means either this can be 0 or this can be 0. Isn't it? So if I take C2 equal to 0, okay, C2 is a constant. It does not depend on x. Okay, so if it is 0 at one point, it has to be 0 at all points. Okay, so at every point C2 is 0. Okay, already C1 is 0. C2 also becomes 0 means Ez component will get, right, completely vanished. Okay, so there will be no component of Ez. Okay, Ez is completely becoming 0. So which should not happen, isn't it? So Ez cannot be 0. Okay, if C2 equal to 0, then my Ez will become 0. Ez will become 0, which should not happen. Okay, so this cannot become 0 because there should be wave propagation. Hz is already 0. If Ez is also 0, that means there is no field component along z axis. That means there is no wave propagation along z axis, which is not possible, right? Wave is propagating. So Ez cannot be 0. That implies C2 cannot be 0. So we can eliminate this condition. So therefore, what I get is sin AD is equal to 0. Okay, sin AD is equal to 0, or I can write AD to be a multiple of pi. Okay, AD should be a multiple of pi. So which implies AD we can take it as a m pi, where mn is an integer multiple. M is an integer. So if I assume m as an integer multiple, then I can get AD equal to, right, m pi, or A is equal to m pi by d. Okay, so the value of A we can derive it as A is equal to m pi by d. So using the second boundary condition, we got A is equal to m pi by d. Okay, so therefore, right, so from the first boundary, we have two boundary conditions, right? Just a quick recap. We have two boundary conditions for the planar waveguide. So what is a boundary condition? The electric field is discontinuous, or electric field will become 0 at the plane, at the conducting boundaries. So I have two conductors, one at x equal to 0, other at x equal to, right, d. So at this place it is 0, at this place it is 0. So Ez is equal to 0 at x equal to 0, Ez is equal to 0 at x equal to d. So I am using these two conditions. Okay. So when I use this, I got C1 equal to 0, and when I use this, I got the value of A, which is m pi by d. So here C2 will remain, it is a constant value. We'll derive that constant whenever required. As of now, it is not required. Okay, it represents the amplitude of the wave component. Okay, basically it represents the amplitude of the wave component. Whenever we go for power calculations, we will also calculate the value of C2. Okay, right. Okay, so this is the thing, right? So using these things, let us represent the final forms of our solutions. So firstly, right, the final form of Ez is Ez is equal to, because now C1 is becoming 0. So what is that we got? C1 is equal to 0. The two things that I got is C1 equal to 0 and A is equal to m pi by d. So I have to put this into the three equations. Okay. So Ez is equal to, so if I make C1 0, so I'll get C2 into sine of m pi by d into x. Okay. So that is equation 1. Then Ex is equal to, again, minus gamma by h square. This will remain as it is. C1 0, so this entire term vanishes. So the other term that I have is A. What is the value of A? A is m pi by d into C2 into cos of m pi by d into x. Okay. So this is the term that I will get. Next, coming to hy is equal to j omega epsilon by h square. This remains as it is. So C1 is equal to 0. So this entire term vanishes. Okay. So what is the other term that I have? Right. So A is m pi by d. Okay. Into C2 into cos of m pi by d into. Okay. So these are my expressions for the various components for a transverse magnetic case. So along with this, we can also add these terms. Ey is equal to 0, hx is equal to 0, and hz is equal to 0. So the 6 components, right? So Ey, hx, hz, all of them are zeros, and the other 3 components that exist are these. Okay, and the expressions are given like this. Okay, so Ez, Ex, Hy. Okay, so I think this is the final expressions. Okay, for the transverse magnetic mode. So I hope it is clear, right? Okay, so we have started with what is a transverse magnetic mode, right? We have taken the planar waveguide structure. From that, we got two conclusions. One, Hz is equal to 0. Other, d by dy is always equal to 0. So using the general analysis approach, we have found out the expressions for the transverse magnetic case. Okay. So, alright, this is about today. So in the next lecture, we will continue with the characteristics of the